I will begin. Dear Heavenly Father, we thank you for this day. And Lord, I thank you for these students, and I just pray you to bless our work today, Lord. I pray. Amen. All right, so let me pick back up on trying to explain the notion of parallel transport, right? So, roughly speaking, the idea is, you're given some curve, right? And, of course, we do this all the time without thinking in Euclidean space. But, if you've got a vector v, right, which is given at the point P, then the question is, if this curve goes over to another point Q, how do you produce this, this vector at P transported to Q? What would that mean? How would you accomplish it? And so we don't even really think about it in Euclidean space because we know what we do. We drill this into head of introductory physics students that it's the same vector whether you put it here or here or here or here or here. And so our parallel transport is just to move the base point and maintain the direction the same, right? So one of the questions we want to answer today is like, what does that look like for a curved space? How do you systematically do that? Because if you're maintaining the vector being tangent to a surface which is curved, it's not at all obvious how to transport the vector, or if there could be a standard notion of that. And then the other very much related thing is trying to describe what a geodesic is and what it means. And he has a great introduction to the idea. He says basically we're trying to abstract what is a line for these Riemannian spaces, right? So how do you look at a line? It's the shortest distance between 2 points. It's what? It's what are the other ways to look at a line? He rattles them off at the start of this section. I've already forgotten, sadly. What's he say here? It's described by two distinct, if you give 2 points, there's a unique line that connects them, right? They're parallel if they have no point of intersection. In Euclidean geometry, one non-vertical line is described by a point in a number called the slope, right? 2 lines are parallel if they have the same slope. In vector three-dimensional geometry, to describe a line, you need a base point and a direction vector, right? 2 lines are parallel if they have the same direction vector. The key notion to this ability, he says, though, is to compare direction vectors at different points in R3, right? So, anyway, this is all hopefully trying to lead us towards the concept of parallel transport. Now, here's the definition that I should recall. We should all recall. And so a couple things to be working with. First of all, C dot, right, of T. The elegant definition he gives of this is it's the push forward under the curve parameterization of d dt. Well, that's lovely. But it's also the sum over I of dci dt partial xi, right? So there it is, another coordinate formula for it. And we define big D v dt as what? It's the sum k equals 1 to n of dvk, v upper k, dt, plus the sum over I and j of gamma, lower ij, upper k, of dci dt, vj, excuse me, all across against partial x k. So what is this? This is the derivative of a vector field v along a curve C. right? So to make sense of this dvk dt, what's that mean? That means that, I mean, it depends on what kind of vector field we're looking at, right? If we're looking at a vector field which is just intrinsic to the structure of the curve, it may be that we've got no vector field we're restricting. I mean, if it is the vector field, if V is a vector field which is defined outside of C, right? So if V was one of these guys, right, and then this is C, then when you're looking at, when you're making this derivative of the vector field V along the curve C, what does dvk dt mean? I mean, if V is a vector field that's over all the whole space, what is this understood to mean? I mean, V is, in principle, the sum over k of vk partial xk, right? And these vk's, these are functions, let's suppose we're on Rn. These are functions from Rn to R, smooth. They're smooth functions, right? They're component functions of a vector field. They're smooth functions. So what on earth does this mean? It means we just look at this part of the vector field. All right? The part of the vector field which is from the curve. In other words, it's not vk technically. This vk would be more pedantically stated v composed with c k of t ddt of that. But it may not be that the vector field has an existence outside the curve. It could be the tangent field of the curve, in which case you wouldn't be able to think about that, you know? Okay, so that's one thing. Now, oh, but he mentions, by the way, dvk dt is equal to sum over k of partial vk partial xi, right, dxi dt, right? But I think that dxi dt would be better written as what, given his usual. I think that's supposed to really be, I mean, I would tend to write CI here, because do you see why I say that? I mean, this is basically the chain rule applied to this comment over here, if I can box it. So if we do the chain rule there, we're getting the derivative of the kth component of the directed vector field. It's functions of x1 through xn, right? And those functions are equal to the ith component of the curve. So anyway, I'm just chain rule. Yeah, definitely the sum over I. Thank you. Very good. Now, definition. If V is a vector field, V a vector field along C, right, which is always a path for us, a parametrized curve that is, then V is parallel to C if big D rather, the covariant derivative, big dv dt is equal to 0 for all t and I. I know we've gone through some of this before, but it bears repeating. Yeah? Agree? So again, what that means is for a vector field to be parallel, for a vector field to be parallel to a curve, it has to satisfy a bunch of differential equations that are related to these connection coefficients, right? What is it?
It was just earlier you stated it's parallel longs. Is that like parallel longs seems to make more sense than parallel to?
Sure. Along is better. Yeah. Yes, along would be a better word. Thank you. Yeah. Agreed. Totally agreed. So, example 5.4.2, which I think I already went through, basically points out that for R2 with G equal to standard Euclidean metric, right? That implies that the gamma I, j, k, they're all 0 because the metric is constant, right? I mean, Gij is actually delta ij in this case. And so the condition big dv dt simplifies to just what? We just get dv dvk dt equal to 0, which implies that v equal to a sum over, I don't know, c by partial xi, I equals 1 to n, where ci is constant, right? Those are the vector fields which are constant along a curve, and I'm forgetting about R2. I leveled my game up. I changed that 2 to an n. It was so much more work. The point is we're integrating dvk dt equals to 0. Integrate both sides. We get vk is equal to a constant for each k. So again, this goes back to my initial statement, which is that, but it's a little bit different, right? I'm just saying that the constant vector fields are parallel along any curve in Euclidean space, right? So that's a backdrop to what we're doing here. Now, I've tried to, your homework, the next one, I made a theme. You may have noticed if you've looked at it. It's all Poincare all the time. Okay, so like I've tried to pick all of the problems that are about the upper half plane with the Poincare metric, because it's two-dimensional, but it's not stupid either. And you know, it's not terribly non-trivial, but it's not terribly trivial. I think it's a good balance. And so like example 5.43 kind of fits in with your homeworks in that regard, because it actually gives you the equations for a vector to be parallel with respect to the Poincare metric. Yeah. What? So 5.43, we had g equals to 1 over y squared dx tensor dx plus 1 over y squared dy tensor dy. And if you work through the conditions, you get dv1. You have to solve these. dv1 dt minus 1 over c2 of t, v1 dc2 dt minus 1 over c2 of t, v2 dc1 dt equals to 0. And then the other one is dv2 dt plus 1 over c2 of t, v1 dc1 dt minus 1 over c2 of t, v2 dc2 dt. So these equations we'd have to solve to find a vector field which was, I mean, given a curve, you could try to solve these to find v1 and v2, which gave you an example of a vector field which was parallel along the given curve. But you see, this is, you can't solve this because the curve is also arbitrary, right? This is just the setup for an arbitrary curve. All right. All right.
Are always C2 except for the right one, the C1? Should they always C2? Are they different curves?
He's got C1 here and here. He has C2 here and here. The reason that there's C2 in the denominator is because of the y squared. There's an asymmetry between x and y in the Poincare metric. There's that 1 over y squared. That conformal factor modifying the usual metric. It makes it interesting. Now, proposition, but by the way, what I'm trying to get at here, guys, is if you look at this, you can probably extrapolate backwards what the connection coefficients are for the Poincare metric. One of your homework problems is to find the connection coefficients for the Poincare metric. They're kind of in here, although I'm worried about typos. There, other place in the chapter, he actually has them stated. If you read the chapter, you'll find the connection coefficients, the gamma 1, 1, 1, gamma 1, 1, 2, and so forth and so on. They're all in there somewhere. But one of your homework problems is to calculate them, right? I'm just saying, you're not alone there. Okay, so here, proposition 5044. For Riemannian space, UG, all right, with Riemannian connection, nada. Let V be parallel along C. Then V has constant magnitude. I can't spell. Magnitude along C. Okay, so what would the formula for the magnitude be of a vector field here? How do you calculate the length of a vector with respect to the metric G? What's the length of V with respect to G? It's the square root, right, of G of VV. I could add a point dependence, but it doesn't really. Let me add a point dependence here. No, I refuse. So instead of looking at that, square it, right? If you can show the square is constant, then that also suffices, right? If the square is constant, it's constant here. So what he does is he says h of t is equal to g, right? And it helps me to think of V as being a vector field which which is defined beyond the curve. I don't know. It just, for me, it makes more sense if I can think of it that way. See, because then we're looking at G, V of C of this, right? And to be even more pedantic about this is G where, what point? At the point C of t, right? That make sense? Man. There's something I don't understand right here in the book. I'm sorry, guys. I'm going to skip over to the next page where it starts making sense to me again. So this much is true. If we have x acting on G VV, we get what? We get G, this is that compatibility, right? G nabla x V comma V plus G of V nabla x V. No, thank you. I think I'm finally, my thick skull starting to penetrate. This is also, I mean, what is this over here in terms of the nabla notation? How would you write that? Nabla sub c dot of t of v, right. So in here, right, we should think x equals to c dot of t. What happens if we think x equals to c dot of t? Right, this is exactly big dv dt, right? Which is assumed to be 0. So this is also 0, right? This is 0. So the whole thing is 0 because g of 0 with anything is still 0, right? So what's that show us? That shows us that c dot, right, of t, this particular derivation, when it acts on this function, g of vv, right, which properly understood is a function of time, I suppose, that's equal to 0. But that being 0 means that the magnitude of v is constant along the curve. I do feel like there's a gap here. I don't know what it is, but I sense that there's a gap here. I can't put my finger on it exactly, but that is close to a proof. This, yeah, I mean, he essentially says that, I mean, he pretty much says that this is equal to dh over dt. He says by the chain rule, but he writes it as x rather than c dot. Anyway, yeah. That's you know that seems fair. Lead derivative of c, he said, of this. of that thing? I think that's true.
Yeah, because I think we used that in 57, right?
Ah, I could look at it that way, huh? The thing that's vexing me, Sam, is that there's this time dependence down here, which is, I have misgivings. I mean, the result is definitely true. I'm just not convinced of this proof at the moment. So I should go on though, because I'm not really the point of what we're doing at the moment. To get into that, I should have just skipped the proof if I was smarter. But anyway, you guys know that I'm not that smart. So now, if you believe this proof, it's not hard to see that if you add another vector field, say W, right? And W is also NW, parallel, along C, then V has constant V and W, right? Fine, constant magnitude along C, and the angle with respect to G between V and W equals to a constant. So the angle doesn't change. Angle is constant along C. That is essentially, all you do is put a W here. And so if this other proof isn't wrong, then this one is also good. Where was I? Oh yeah, W. But see, V and W are both parallel, so they're both 0. So the metric of V and W is constant along the curve. Since they have constant magnitude by the first theorem, that implies that the angle between them, as judged by G, is also constant. So what that says is that, if you have two vector fields along a curve and they're parallel, then the angle is constant. It stays the same as you look at these parallel vector fields to the curve. All right? Does that make sense? Like that. And then he looks at the he does something unpleasant. He does an example. Oh, but before that, he actually tells us the theorem that I should state. Here's the theorem. 5.46. And what it says is that if you have a Riemannian space with a connection as usual, Riemannian connection, and if you have a curve which say goes from the unit interval 0 to 1 to U, the Riemannian space, with suppose C of 0 is equal to P. He says let V naught be tangent to the space at P. All right. Then there exists a unique parallel vector field. All right, parallel vector field V along C such that V at 0 is equal to V naught. Again, the vector field along the curve, you can insert time into them, right? So V of 0 makes sense. The vector field V is called what? The parallel transport of V naught along C. No, he does not give the proof, nor will I, but as all of these theorems are, they basically boil down to sorting through the manifold theory and relying on the fundamental existence and uniqueness theorem of differential equations. It's always that. But the precursor to this theorem is the ones we just did on the other board, right? I mean, you can kind of understand what's going on here, right? You start out with one vector, and you look at another vector of the same length along the curve, right? You can, well, no, I can't say that. I mean, you actually have to look at the, given a curve, you look at these differential equations, right? Set them equal to 0, and because they're nice enough, you can find a unique solution that has that initial condition, that v of 0 is v naught, right? And solving the differential equation means that the vector field's parallel along the curve, right? And that's the parallel transport. What makes the previous two theorems interesting is that if you have a curve, right, and you start out with my point P, right, and you start out with a vector v naught, and you start out with another vector w naught, right, you can look at the parallel transport of each of the vectors separately, right? And so, I don't know, I need some notation for it or something. What do you guys want me to use? I don't know. Parallel transport. That's a bad notation. Parallel transport of v naught. Parallel transport of v naught to c of t. There you go. There's a horrible notation, since I can't think of anything better. You compare that to the parallel transport of w naught at the same point on the curve, right? And what's the situation going to be? The situation is going to be that whatever the angle was here, if that angle's theta, this angle's still theta, right? So if you can parallel transport 1, you can parallel transport 2, and it'll give you a way of comparing vectors at different points on the manifold, Riemannian manifold. Yeah?
The V naughts and the W naughts are supposed to be, those are parallel to each other, right?
No. I just taken two vectors in the attached to the curve C and tangent to the manifold that we're looking at, tangent to the Riemannian space we're looking at.
So it's more like it remains parallel to itself, other instances of itself over time.
Let's see here. So if we could take a more interesting example, something like this. If I could talk about parallel transport of vectors on the sphere, for example, I could start out at the north pole with the pair of vectors. I could let this be v naught, and I could let this be w naught, like that, And I could imagine parallel transporting them with respect to some metric and corresponding connection on the sphere. There's not just one. We can give the sphere different metrics, in fact. And correspondingly, the sphere can be given different geometries. Just like we've been looking, all of the examples in this chapter are about the plane. Almost all of them, they're about R2. But we're giving R2 different notions of distance. That also is true for other sets. The geometry, it's not just governed by the point set. It's the set of points paired with the metric. That's what determines what geometry is, what your notion of distance is between points, angle between vectors, all that stuff. Now, if you insist that the metric on your space be given by the restriction of the larger ambient Euclidean metric, like if you insist that the metric on the sphere be the restriction of dx squared plus dy squared plus dz squared to the sphere, to the sphere, then that, goodness gracious, I don't know what I just did, but maybe it's this marker. That is not ambiguous. The restriction, if you give me a point set inside Rn and you say I'm going to give it the induced metric from the ambient Euclidean metric, that's not ambiguous. That gives you a particular, and that's what your intuition is all geared up to talk about. You know, curved spaces have curved metrics. I mean, it's weird that you can take a sphere and put a flat metric on it. But you can do that. You can look at the stereographic projection of the sphere onto the plane, and if you pull back the flat metric on the plane to the sphere, that gives you a flat sphere. Which is weird, right? But you can do that.
Flat sphere minus a point.
Minus a point, right. Now, anyway, so whatever my notion is of parallel, if whatever my parallel transport is, I don't know, maybe it's such that V naught ends up being parallel transported to that. And if you don't mind, I'm calling it V naught prime. It occurs to me I could do that. And then, you know, W naught, well, what I do know is that, once I sort through this notion of parallel transport, if I start out with a pair of vectors on the sphere, which is, they have to be in the tangent plane to the sphere, and if I start out with them perpendicular, I'm going to end up with them perpendicular, all right? And then you can keep going here, right? You could think about then transporting those guys over to here, right? And maybe, I don't know what it is. It's V naught prime prime and W naught prime prime not to scale. And then you could think about transporting them back, right? I mean, you could actually think about, or you could think about just one vector parallel transporting it around a loop, you know? Here, let me make it simpler. Suppose this is a loop on the sphere. I start with a vector V naught, right? I parallel transport it around this loop. With respect to some connection on the sphere, all right? And then I get back to here, like that. When I get all the way back around, my parallel transport actually doesn't have to agree with what I started with. This is called holonomy. Holonomy is the angle between the vector that you started with and the parallel transported vector around the loop. Okay. Yep.
So the relationship between everything is that it's orientation.
Between what? I just didn't hear you.
Or the relationship between, say, like V naught is angle between V naught and W naught if we're following the approach 5.1, and its orientation with respect to the curve itself and the angle that it has, like that's tangent, so it stays tangent around the entire circle.
Well, it doesn't have to stay tangent. I mean, there's lots of different situations that the vector could. The thing is, this doesn't assume anything about V naught as it relates to the velocity to the curve. The velocity to the curve can be any different which way. V naught can be any different which way. But this says that there's a specific way of starting with V naught and then pasting on the next vector, and the next vector, and the next vector, and the next vector along the curve, such that its derivative, its covariant derivative along the curve, it remains 0.
So it's the angle of the curve.
Yeah. Now, some of your questions will start to get answered by as we go on in this section. So let me go on. Maybe this example would help, actually.
So if we have that angle between V naught and V naught prime when we go around the loop, that's not 0, does that mean that it can't be an induced metric? So the Euclidean metric is
No. In fact, no. It doesn't say anything about whether or not it's induced. It does say something, though. Example 5.47. But obviously that's interesting, right? I mean, that's something that does not happen in Euclidean space. If I look at parallel transport in Euclidean space of a vector along a curve, it's very boring, right? Like this I can do without differential equations. Pick me any curve you like, take any vector you like, and then parallel transport. It looks like I did this last time, right? It's just dumb. Yay. So we get back to here, and all the way around, they're equal, you know? It's just silly.
But there's some metrics that you can't use Euclidean space using.
Well, that's the funny thing is I'm telling you for a sphere, even though it's induced from the Euclidean metric in R3, the fact that the sphere is not R3, that it's the sphere, will cause the holonomy to be non-trivial.
Right, but I'm saying are there some metrics that you just can't induce from the Euclidean metric at all? There's just no points that you can take that would make that.
Is there some metric that you can't induce from the Euclidean metric? I think actually no.
Is that specific to Riemannian geometry, or is that?
I think it's specific to Riemannian geometry. These are the deep embedding theorems of Nash. Like Nash found these theorems in the 50s that if you have a Riemannian space, you can find an isometric embedding of that space in Rn sufficiently high. Isometric being something we should get to shortly. But basically meaning that you have the same Riemannian manifold up to smooth, distance-preserving map. Yeah. So in some sense, always working with extrinsic geometry isn't such a bad idea because Nash's theorem says you can always look at it as extrinsic if you want. And yet we don't. So anyway, but Nash's theorem may not be totally general. I don't really know why. It is pretty general though. And okay, anyway, getting to my point here. If we look at the metric with the matrix 1 plus, this thing we worked out, remember? This one we actually worked out, this guy, which was what, the paraboloid? The pullback metric of the paraboloid to the plane, I want to call it. This thing, here's the matrix of it. Then if you use the connection coefficients, which we got, in particular gamma 1, 1, 1, which was equal to gamma 2, 2, 1, which was 4u over 1 plus 4u squared plus 4v squared, etc., right? In this case, the differential equations that we need to solve for parallel transport are these. v1 dot plus 4t over 1 plus 8t squared, v1 plus v2 equal to 0, and v2 derivative plus 4t over 1 plus 8t squared times v1 plus v2 equal to 0. These are the differential equations. These are the parallel transport equations that you have to solve to actually describe parallel transport on the plane with the pullback metric of the paraboloid. And he actually works it out, and these have solution. In fact, v of t. Let's see here. Now this may be, I may have missed the fine print here. Oh yeah. This is for a given curve. I mean, you're like, that's too good to be true. It can't be like arbitrary general parallel transport. You got me. You're right. It's for c of t equal to tt. 0 less or equal to t less or equal to 1. That's what, given that curve, that's what these monstrosities simplify down to. You see, you get the dc1 dt are just 1, so you literally just get, and then the gamma, these become t's, so you get 8t squared, you get 4t. You can kind of see what's going on even. You have to evaluate the connection coefficients at the curve. In other words, you set u equals to t and v equals to t to get those equations. And he actually solves them in the book. I won't even write it down. It's not really important what exactly it is. The point is you can solve them because he probably backwards modified. I'm not sure. I'm very suspicious of examples like this in the book. they start with the question, how can I make differential equations that I can actually solve and come up with an example for students, as opposed to, anyway. No, I'm not against, I'm not saying anything against it. I'm just saying usually these are really hard to solve. All right, so finally, getting back, hopefully this time with a little bit more understanding to the definition of geodesic. What is a geodesic? Parametrized curve. Again, for a Riemannian space UG with metric connection nabla, a parametrized, and this is something important to notice, that the notion of geodesic involves parameterization. A parametrized curve C going from I, and we're dealing with a domain, but of course this can be adapted for a manifold, is a geodesic if what? If nabla C dot is equal to 0.
That just be IT or
What'd I do?
you said I to Rn is U a subset of Rn? Or
Oh, yeah. We can say U. That I think that's better. I like that more. At least we throw in the possibility it might be something other than Rn. Because this would still make sense in that context, provided we defined connection in that context. If you're willing not to sweat the details, I'm willing to include some more interesting examples. But so in the other notation, of course, this says what? D C dot dt is what? 0. And I think I told you last time, it's like 0 acceleration, right? Okay. So this is what it means to have a geodesic. It means its velocity, right? Its velocity is what? It's constant, right? The velocity of a geodesic is constant along itself. See that? The velocity field C dot is parallel to the curve, right? That's why this is a reasonable generalization of what it means to have a line. Because a line is one that its direction vector is constant, right, along the curve. So this is the next best thing. Now there are all kinds of theorems that are known for geodesics, right? And let me look them up here. Oh man, stink. I was hoping I'd get farther today. Of course, first of all, what are the geodesics in Euclidean space? Right, just line segments. Because the condition just reduces to the second time derivative of each component of your curve is 0. When all the gammas are 0, it just reduces to that. So we integrate twice, we get line segments. But line segments parametrized, it's important that they're line segments of the form like x naught plus at, y naught plus bt in the plane. Like if you took your line segment and you parameterize by a non-constant speed parameterization, that's not a geodesic anymore. Yeah. Now, theorem, I'm just going to read it if you don't mind. Let UG be a Riemannian space for each point there is a domain. So basically the theorem says that you can, if you've got a Riemannian space like this, right? And you take a point P and you take another point Q right? Then you can pick a domain. In other words, kind of a universe inside the space, say small enough, such that there's a geodesic which connects those 2 points. All right. You can find a geodesic from P to Q, right? And call that L naught. And if you take any other curve inside that domain which connects those 2 points, like L1, well then the length, suppose that L naught and L1 are the lengths of the curves, then L naught will be less than L1. So they're minimizing, they're curves which minimize the distance between points. But you got to be careful, right? The reason that you have to say there exists the domain is because, like I told you guys last time, if you think about the great circle and you think about these 2 points, think about this as part of a sphere. If you look at this as your P and your Q, well then there's a geodesic, there's 2 geodesics that connect these, right? There's this one, let's say, but there's also, well, I use different color, this one, right? And they're both they're both geodesics, and they both connect P and Q, but one of them is minimizing and one of them is not. If you were to focus on, but if you make the picture a little bigger, and so you imagine some kind of, if you can imagine me drawing behind the board, make some like little domain that connects that includes the 2 points. You can find an open set small enough that inside P and Q, the geodesic which connects P and Q is the unique length minimizing path between the 2 points. And also, I don't know if he describes this or not, but you can use the metric to define a metric as in distance function on a Riemannian space. So how would you define like distance between 2 points in a Riemannian space?
Just take the length of the geodesic.
I think you could do that. Interesting. I wasn't thinking of that, but that seems like a good thing to do. But you could do this. But I think you're right. The distance between P and Q would be the infimum of all lengths of paths that go from P to Q. And that also, and it also takes into account like fuzzy edges, because sometimes there are pathological cases it takes care of. Anyway, I don't want to get into that because I think that more properly belongs to a proper course in Riemannian geometry and all that. I mean, you'd spend a day or something on that. But long story short, any Riemannian manifold can be made into a metric space in the sense of analysis. So there's that. It's kind of nice. Now, so there's a unique geodesic, and that's it. That's about all I have to say about geodesics for you guys. I think after you work through the homework problem on parallel transport and geodesics, it'll sort of come to life more for you. I hope you see how these things reduce to that notion that we have in Euclidean space of just moving vectors around. It's kind of the boring case. But then then I read the rest of the chapter, and I was looking for something and looking and looking and looking, and I never found it. And it's not in his chapter, and for shame. I'm disappointed that it wasn't in this. I haven't found it. Maybe it's there somewhere. I haven't found it yet. But next we talk about curvature. All right? So let's talk about curvature. I actually don't have much to tell you guys about curvature. I've been thinking about this, and I think if there's any topic in here that doesn't really warrant too much discussion, it's curvature. Mainly because I don't think I really want to ask you to calculate curvature of a 3 or 4 dimensional manifold in here. I might have asked you a 2-dimensional case. In that case, we have theorems which reduce this as he quotes Mikhail Gromov. He said that the curvature is a little monster of multilinear algebras whose full geometric meaning remains obscure. I mean, it's a 4-slot tensor that is involved in building. It's a 4-slot tensor built over the back of the connection. It's kind of the highest ranked tensor I know of that meaningful things are done with. And there's about 3 billion different ways to look at it. And they all, at the end of it, there's like three or, it seems like there's at least 3 distinct ways to reduce back to the classical differential geometry of Gauss. And I've given you homework problems that will help you connect with some of the ideas about the curvature in this book and the formulas of Gauss. Gauss, again, took an extrinsic viewpoint. And basically what Gauss did was to understand how a space was curved. Here's what he did, roughly speaking. You look at your manifold. I mean, well, really surface, right, inside R3 to start with. And so if you look at this and you want to tell how it's curved or not, what you can do is look at, you've got UV coordinates in there somehow. You've got normal vectors. So you got the normal vector field. And so to decide how curved or not curved your space was, basically you can study the mapping that takes these and puts them over in the unit sphere. You can study how to map the normals. You can study how the normals map to over here on the unit sphere, or something like that. So to give the sort of most transparent example, if you look at a quarter sphere, right, and you look at the normals to that, normals to the quarter sphere, they're kind of boring because they are the points, right? And then if you look at the direct image of these normals over to the sphere, well, it's actually the quarter sphere. And so roughly speaking, that tells you about the curvature of the space, because how much of that you're filling out has to do with how curved your space is, right? The more the normal sort of moves around, the more curved the surface is. And you can make this precise. And this is roughly speaking the idea of classical differential geometry. Anyway, in contrast, the curvature is the following: r of x comma y, it acts on z, and it is acting according to the rule nabla x of nabla y of z minus nabla y of nabla x on z minus nabla of the Lie bracket of x and y acting on z. So this is actually, he points out this. He says R of x, y is actually a mapping from vector fields on U to vector fields on U. And then, of course, so it's given by this, but then of course we can, in fact, define the 0,4 tensor, R, X, Y, Z, W, as equal to G of R of X, Y of Z with W. So this R is a 0,4 tensor. Here, I'll give you the actual formula for the. You should at least get to see the formula for the components of the curvature. Here's the formula. So this is the analog